Bismillahirrahmanirrahim. Assalamu alaikum everyone. In today's lecture, we'll be discussing about rectifier circuits. So we are moving into the next category of converter circuits. That is, we'll have sources of AC types and we'll having output power or loads of DC type. So for that we need an interface power electronic converter which can convert the power available from the AC source to be delivered to the DC type of load. For that, the converter circuits that we use are commonly known as rectifier circuits. Okay, there are two main categories of rectifier circuits. The first category of rectifier circuit is termed as uncontrolled rectifiers. And the next major category of rectifier circuits is termed as controlled rectifiers. So what is the difference between the two categories of rectifier circuits? In the case of uncontrolled rectifiers, a certain device which is used as a switch to convert the input AC power into DC power is of such nature that it cannot control the flow of that power. If you recall from the discussion that we used to have in the case of DC to DC converter circuits, we had like some certain power electronic converter circuit which employed a switch which was under the influence of external control. Okay, so in that we used devices as switches, for example transistors, which could be controlled by some external source or external signal, while at the same times we had devices, for example simple diodes, which we had mentioned or discussed that these are uncontrolled devices, means which cannot be controlled by some external signal or pulse, or they are only under the influence of the applied voltage across them. So same is the case here, the rectifier or the converter circuits in which we employ diode as a switching device, those are termed as uncontrolled devices, because as we are now familiar that the case with diode is that it cannot turn itself on and off under the influence of any external signal, but it can only be turned on and off by the polarity of the voltage that is applied across it. While in the case of controlled rectifiers that we'll be having over here, instead of diode we'll be employing thyristors. In the case of thyristors, we know that these are devices which operate similar the way a diode operates. The only difference in this case is that we have an external control pin available in the case of thyristors, and basically with the help of that control pin we can control the turn on and turn off of this thyristor. If you just have a look at the symbol of this, so this is that control pin that is available in the case of thyristor to us, that as long as we do not have any control pulse being applied to this control pin, so this device, this thyristor, will not be turned on. Okay, so that is how we can actively control the flow of power with the help of a thyristor. So these are the two major categories of rectifier circuits that we will be discussing. The rest of the operation of a system or a circuit in the case of an uncontrolled rectifier and a controlled rectifier remains the same. The only difference is that the moment or the phase angle at which that device or that circuit is going to be turned on In the case of diode, that is like only dependent on the voltage polarity across the diode terminals, okay. And in the case of thyristor, it will be also dependent, that not only it will depend on the voltage polarity. So in this case, the control feature is only the voltage polarity. While in the case of thyristor, now there are two things. One is the same, that is the voltage polarity, and the prerequisite for this voltage polarity is the control pulse that you can apply across the thyristor. So means if there is a voltage, for example, if it is positive over here and negative over here, but you do not have this control pulse, so this device will not be turned on. But if you have this polarity and then there is a control pulse applied across this one, so that will result in this device to turn on and start conduction. So that is the major difference between uncontrolled and controlled rectifiers that we'll have. The further categorization within the category of rectifier is that we'll be discussing, for example, simple half-wave rectifier circuits. Then we'll be discussing the full wave rectifier circuits. And in this full wave rectifier circuits, or even in the case of both either half wave or full wave rectifier circuits, we can either have single phase rectifier circuits, okay. In both of these categories, we can either have single phase rectifier circuits or we can have three-phase rectifier circuits. Because now you know that in this case we are having AC voltage as the source, so it can have its type as either a single phase or it can have its type as a three-phase, okay. I'd let you know that half-wave rectifier circuits that we are going to discuss have very limited applications in practical or in industry, but we discuss them over here because these are the simplest one to start with. And once we like grasp a good idea or a good concept of these rectifier circuits, so that helps in the understanding of the full wave either single phase or three-phase rectifier circuits very much, okay. So that is why we begin with this one, and then we will gradually shift towards the single phase and then finally towards the three-phase rectifier circuits. So as you all may be familiar, but we'll just quickly go through this one. That is the simple and the basic category of the rectifier circuits. That is termed as a half-wave rectifier circuit. So in the case of a half-wave rectifier circuit, we will have this simple circuit. We do have an AC voltage source on the input side, okay. Then we need to have like some certain device which should be working as a switch, and then if we can consider a simple DC resistive load, okay. The discussion that we'll be having on this half-wave rectifier circuit will have different subcategories, and that is it will have different types of loads, that which type of load we are considering, whether we are considering a purely resistive load, then there will be a next category in which we will have a practical that is industrial load, that is inductive load. This one is termed as R type of load, the other one is termed as RL type of load. Then we'll have another type that is termed as RLE type of load, in which we'll have a combination of series resistance and inductance plus some sort of voltage source. What is the practical application of that? We can consider to be having a battery on the output side or on the load side, so that will be represented by a voltage source here in the discussion or in the textbook. Okay, so we begin with the simple one with which we are all already familiar, but just to quickly recall the basic concepts related to this one. We'll go through this one. I will introduce some basic performance analysis parameters in this one, and then we'll continue that discussion for different other types of loads. So as I mentioned that in any power electronic converter that I had initially given the name of this abbreviation, that is PVC, we need to apply some certain type of device as a switch. So here on the input side, if I draw the waveform of this voltage signal, okay, so we'll have something like this. This may not be exactly according to scale, but anyways, for understanding, I hope you will get the idea. This is the source voltage represented by Vs over here. Okay, so we need to have some certain type of device because we are considering that our load is of DC type, okay, and only unidirectional or DC current should flow through this load. So we need to apply something over here that should allow the current to flow only in the one direction, that is positive direction in this case, and should block the current in the negative or reverse direction. So since we have studied the different types of switches and we are familiar with the characteristics of switches, that a device which allows only the current to flow in the positive direction and blocks the current in the other direction, that is a diode. So we can simply replace a diode over here as a switching device. Okay, so what will happen that as soon as this source voltage goes above 0 and it gets sufficiently higher than the forward voltage drop across the diode, so immediately this will start conducting and we'll have some voltage available across this resistive load. So this will be the direction of the current flow through this circuit. Okay, so if you want to draw the voltage that is available across the load or across the output, so we know that exactly this voltage or this waveform will appear across the output voltage as well. I want to label these waveforms, so these are the positive and negative maximum values of the output voltage. Then we can label this axis either by like time axis, okay, but in case of these discussions related to the rectifier circuits, as we'll see that need to have different calculations a bit later. Okay, so we can also say that this is the end of this cycle and this is the complete time period of this one. But since we know that this waveform is of sinusoidal shape and we do have its representation in terms of its mathematical equation as well, that is Vs is equal to so here we can either like simply write t over here in this parenthesis, okay, and then we need to have like a substitution of the phase angle of this one as well, okay, and a more appropriate representation of this one is to write this one as omega t. So basically this covers it in terms of its angle, that what particular angle currently this sinusoidal wave is at, so that basically helps us in doing certain analysis. So that is why throughout this discussion that we will be having, we'll represent this axis with the help of omega t. Okay, that is the radian or the angle of this particular sine wave. So since now we are having this discussion in terms of its angle, so we can mark these key points that a sinusoidal wave completes its cycle in 2 pi radians. Okay, this is the half of the cycle. So according to these, now we know that from this interval which ranges from 0 to pi, this sinusoidal wave will have a positive magnitude, and during the rest of the half cycle from pi to 2 pi it will have a negative magnitude. Okay, so we know that diode will remain forward biased. We can assume that this diode is ideal, so even during this positive half cycle we can assume that it is behaving as a short circuit. Okay, so during this positive half cycle what will happen that the entire voltage that is being applied by this source. Okay, we can ignore if there is any difference between these waveforms, and we can consider it to be exactly the same as the input. Okay, so this is applicable for the positive half cycle, that all this voltage appears across this resistive load during the positive half cycle, while during the negative half cycle, since as soon as the polarity of the applied voltage changes, okay, so then we'll have like opposite polarity signal over here. Okay, and now we'll have a higher voltage positive over the negative or the cathode terminal with respect to the anode terminal. So this will mean that now the diode becomes reverse biased and it behaves as an open switch. Okay, so it will not be able to conduct anymore and will not have any current flow through the diode. So that will mean that the voltage across the diode in this particular case is going to be 0 from this interval pi to 2 pi. Okay, so that is how the output voltage across the diode will look like. Okay, one more thing that I would like to add over here that is necessary to be explained and necessary to be understood at the same time as well, that how about the waveform of the current or the value of the current. Just in a while we'll have its calculation as well. Okay, but before going to that, I want you to just have a look at that over here as well, that the value or the shape of the current waveform will also be exactly the same as this one. Okay, so basically there can be a difference in the magnitude of the current. Of course, that will be slightly lesser than the voltage in terms of magnitude, because that is the ratio of voltage to the load resistance. Okay, but the shape of the waveform will remain the same as the output voltage, and that output voltage will be exactly of the same waveform, because we are considering an ideal diode. There will be no voltage drop across the ideal diode. Okay, so it will have the same value as the source voltage or the input voltage, and the current will be slightly lesser than that, but the waveform will remain the same. It will follow the waveform of the current of the voltage. So because later when we consider the next case, that is of an inductive load, or finally of the RLE type of load, so then there will be a serious difference between the current and the voltage waveforms, because now we'll have those concepts of leading and lagging, because we are dealing with AC quantities now. Okay, so we need to take notice of this information over here. Okay, okay, before moving forward and concluding this discussion about the half-wave rectifiers waveforms, I would just like to mention that we have had this discussion before as well, that the key thing in understanding these circuits is to have a very clear idea about the voltage and current waveforms about each and every component of the circuit. For example, if you just recall from the discussion that we used to have in case of DC-DC converter circuits, that we used to have like all these waveforms for the inductor voltage, inductor current, the capacitor voltage, capacitor current, the source and output waveforms for voltage and current, and then even at times you would need to have a clear idea about the waveforms across the switch or across the diode as well. We did not needed them so much in the case of the discussion for DC-DC converters, especially in the continuous conduction mode. But if you recall the discussion from the discontinuous conduction mode, so we used to have that discussion about the diode waveforms as well. So in the same way, I would just like to plot or let you think about that what is the voltage waveform or the current the waveform of the voltage which I have labeled as VD over here is going to be across this diode. Okay, so it is simple, but we just need to like have a look at this as well, that if I want to plot for the same interval, that is from omega t that is from like 0 to pi and pi to 2 pi, if I want to draw the waveform for VD, that is the voltage across the diode. So how is that going to look like? Okay, so it is very simple. During the positive half cycle, as I mentioned, that we are considering ideal diode, so there will be it will be behaving in the forward bias mode and will be effectively a short circuit. So there is zero potential developing across any short circuit device. So what will happen, that we will have no voltage appearing across the diode during the positive half cycle. During the negative half cycle, we can see that the diode will behave as an open circuit. Okay, we can consider these 2 points that these are now open, and like effectively there is no diode present over here, and this is the voltage of the applied polarity during the negative half cycle. So we can see that like since there is no flow of current through this path, okay, so effectively all this positive polarity or this voltage that is appearing from this source will be present across the diode, because there is no flow of current, okay, so no voltage is dropping across any component, and total voltage that is being applied by this source during the negative half cycle will be present or will be applied across this diode in the negative half cycle. So effectively whatever is over here during this negative half cycle, that will be present across this device, that is the diode, okay. So this will be effectively the same as we are having it over here during the negative half cycle. So that is what we will have in the case of a negative half cycle. So you can also see it more clearly in the textbook that we'll be using for the discussion related to the rectifier circuits. Basically we are going to use you can use different books that you have been like using up till now, but we are switching from the one that we have been using for the discussion of DC-DC converter circuits, okay. You can either use the textbook that was written by Daniel Hart. It is, I think, chapter number 3 of this book that begins the discussion of half-wave rectifier circuits, or the other one that I just showed you a while ago, that is power electronics, converters, applications and design. That is by Ned Mohan. Third and fourth edition are available of this one. You can use, that is third edition of this one. Soft copy of this is also available online. I also have it. I'll see if I could share it on the MS Teams platform as well, okay. So, and this is chapter number 5 in this book, chapter number 3 in the case of Daniel Hart, and this is chapter number 5 in the case of this particular one, that is the author name is Ned Mohan. So you can also see the waveform of this half-wave rectifier. This is like you can see from this equation number, this is chapter number 5 of this book of Ned Mohan, that we have this simple half-wave rectifier circuit as we can see over here, okay. And this is the waveform, this one, that is of the source voltage, as we can see over here, Vs, okay. Now this waveform that only is available over here in the positive half cycle, Vd, they have given it the voltage across you can say the load, okay. So this portion only of the source voltage is available across Vd in the positive half cycle, while this portion, as we can see over here, given the name of V diode, is available across the diode during the negative half cycle. And this, what I had mentioned, what I was emphasizing on, that we need to take a note of the current waveform as well, that the current waveform is exactly like having no lag or no lead, that is in phase with the source voltage. So this is the current flowing through the resistive load, so it is in phase with the load. Definitely the value, the magnitude is lesser than that. We'll see the equations in a while. And during the negative half cycle, the current stays 0 and the voltage also stays 0. So you can see Vd, which is the voltage across the load, that is 0, and the current across the load is also 0. Okay, so now if you want to have the calculation of some of the basic, for example, parameters, some performance analysis parameters. These parameters basically do the same job in the case of rectifier circuits that was done for us by, for example, this conversion ratio M of t, Vs by V naught, or V in by V naught in the case of DC-DC converter circuit. That basically this equation used to tell us that how much of the input voltage or what is the value of conversion ratio, that how much the source power is available and how much it has been delivered to the load. So in this case, in the case of AC-DC converter circuits, we'll have a few parameters in order to analyze the performance of a circuit. This is important because we'll have like different type of circuits and a few of them will be doing the same job. So this will basically help us in establishing that difference between different type of converter circuits. That, for example, if I'm saying that a half-wave rectifier circuit converts an AC voltage into DC, then a full wave rectifier circuit also does the same job, and then even a three-phase rectifier circuit. And further in the three-phase, we'll have these categories of half and full wave as well, or controlled and uncontrolled as well. So we need to determine that like what is the reason if a half wave rectifier circuit can do a certain job, and then we need to switch to a full wave rectifier circuit, or even we need to switch to a three-phase rectifier circuit. And if all of them are doing the same job, so then what is the difference? So basically these performance analysis parameters will let us know that what is the difference. Okay, so one of the performance analysis parameters is the average value of the output voltage. So as we saw the waveform of the output voltage in a half wave rectifier circuit, so basically we need to have some formula available, because only just by looking at waveform we cannot determine that actually how much of the input AC voltage is available or has been converted to a certain amount of output voltage. So that is what the average, or which is also commonly known as the DC value of the output voltage. So we need to determine that value. So what is the procedure of calculating that value? Because if you remember that the waveforms do not tell you the complete picture, that this was the value of the waveform of the source voltage that we had available. Okay, this is for the source voltage, and what did we had at the output, that is across the load, that we had this waveform available. Ignore if there is any difference, consider that we are having the same shape for input and output. This is the peak value, and this is for the output voltage, that is, you can term it V naught or VD, whatever. So we need to know that how much of this has been transferred, or how much power has been transferred. So one way of doing is that we need to calculate the average or the DC value of the output, so that can tell us the effective value of the power that has been transferred to the output side. So the formula for calculating is the same as we used to calculate for the average of such type of waveform. Since this is a continuous signal, so we need to take we need to determine the area that is under this curve, and area under the curve is determined by using the integral equation. Okay, since this is the average, so I always I tell my students that the simplest way of doing this is by using this simple mathematical equation, that is, we need to determine the total area and need to divide it by total time. Okay, so for the output voltage, what do we have? The total time that we have available, that is this one, because we also need to consider this portion. This is equal to actually this is equal to 0, so but for the sake of analysis we can consider it in the beginning. So this is the total time period of this signal or this function, so we can call it 1 over t. This is the total time, and the total area that we have to determine can be determined by using the integral equation. So this integral starts, or should have, the limits of starting at 0 and ending at 2 pi. Okay, and then we need to have the output voltage signal during this interval, and this is the argument of it. or even we can replace it by t of this total time in the beginning as well, because these are the limits of this total time. Okay, next we can make substitution into this equation. Okay, that the total time period of this signal is equal to 2 pi. So this is why we need to mention it in terms of t, because otherwise it will create a confusion that the total time period of this signal is only from 0 to pi, and we'll completely ignore this portion. So this is why we need to like have our basics clear first, that why we are mentioning 2 pi over here. If we write this directly, so it may be like confusing that why we are not using the limits from 0 to pi over here. Okay, it will be clear with the help of this step as well. Now further we can see that this signal is divided into two portions. Okay, we are having a particular shape over here during the half interval, that is from 0 to pi, and it is having a value of 0 during the rest of the half interval. Okay, so that is why now we need to divide this integral into two half sections. The value of V naught is equal to this waveform, that is of the source voltage. Okay, so now we cannot write it V naught over here because it is equal to this particular signal, that is equal to Vs, which is having, I have already mentioned that this Vs is equal to Vm sine omega t. So this is the reason that we had mentioned this omega t over here, because this signal or this function is dependent on the value of omega t, that for different values of omega t will have different values of the output of the source voltage, that is Vs. Okay, for example, for omega t equal to 0 we'll have this source voltage equal to 0, and for value of omega t equal to pi by 2 or some other, we'll have a different value of Vs. Okay, so that is why we have made this as a function of omega t. Okay, so for this positive half cycle, that is for these limits from 0 to pi, this is having a value and then for the remainder of the half cycle, that is from 0 to pi, this one is having a value of 0. Okay, so this complete function will turn into 0 because of this constant value, that is of 0, while this can be evaluated now easily. Okay, once we do the evaluation of this one, so we can come to this function finally. This is the DC, or the average value for a half wave rectifier circuit. So you can just remember this value, and then we will see that when we have the calculation of this same performance analysis parameter for full wave rectifier, so what will be the value of that in the case of a full wave rectifier circuit. I'm sorry, excuse me, this function comes out to be Vm divided by pi only. We do not have this factor 2 over here. This will be present in another equation. Okay, so this is what we will have in the case of because if you evaluate this integral, so it comes out to be like 2, so this will cancel with this 2, and that will result in a final equation of Vm divided by pi, or you can also write it 0.318 pi. If you evaluate 1 over pi, so that will lead to 0.318. Okay, okay, so this is about the DC value of the output voltage. Okay, if you want to calculate the DC value of the output current, okay, you can term it either IDC or I average, both are okay. Okay, so that will be simply equal to the DC value of the output voltage that we have just evaluated divided by the value of load resistance. We can substitute the value of the DC value of the output voltage, that will be equal to this factor. Okay, similarly there is sometimes another requirement, that is to calculate the RMS value of the output voltage or the output current signal. So the equation of that is slightly different from this one. For that, we need to recall that what does this word RMS stand for? That is the root mean square. Okay. So we need to take the square root, we need to take the mean or the average value, and then we need to take the square. So this is normally which is performed first. Average, for example, we want to calculate the RMS value of the output voltage. Okay. So first of all, we need to take the mean value of that, we need to take the square of that mean value, and then we need to take the square root, or which is has been represented by this letter R or root over here. Okay, so the average value we have just evaluated. Okay, we want to write the complete equation, so we can write it in this way. We don't need to write the other half interval, that is from pi to 2 pi, because that is already we know that the other half of this integral is equal to 0 from pi to 2 pi. So that is why we ignore that term, or we do not write that one. Okay, so that is why it is not written over here. So we have written the mean value or the average value, that is represented by this letter over here. We need to take the square of the function that we are evaluating, and basically we are evaluating this function. So we need to take the square of this one, and finally we need to take the square root or the under root of this function. So that is, this is how we will calculate the square root of this function. Okay, so if we evaluate all of this integral including the square root, so the final value that we'll have is equal to Vm by 2. This is the RMS value of this signal. So you need to know the differences between the average values and the RMS values. If you remember the DC value that we had calculated just a while ago for this output voltage, that was equal to Vm by pi, while this one is the RMS value of this signal. Okay. In the same way, just as we had the DC value of the current, which was equal to the DC value of the voltage divided by the load resistance. So in the same way, we can have the RMS value of the current, that is equal to the RMS value of the voltage divided by the load resistance. If we substitute the value, so we'll have Vm divided by 2R, and here we'll have Vm divided by pi R for this one. Okay. These are necessary to be known separately, because at times we need to calculate the DC or average power which has been absorbed by the load or the output, or at this sometimes we need to know the power which has been absorbed by the load, that is termed as the effective value of power that has been absorbed by the load. So that is calculated in terms of RMS power. Okay. So along with these, there are some other terms or equations that are also required to be known at times. Okay. So I'll just introduce those terms briefly over here in this lecture. For example, quite often it is required to be known that what is the rectification ratio of a rectifier circuit. Okay, so basically it is the figure of method of comparing the effectiveness of you can say of a particular rectifier, and this is quite often represented by this symbol, that is sigma, and this is a ratio of average power to, you can say, RMS power, and then this is also can be computed in terms of the equivalent values of voltages and currents. So we can say that we'll have VDC into IDC will give us the average power that we have just computed, and we'll have RMS quantities for voltage and current in terms of their corresponding values. Okay. So once we have this rectification ratio, so just as we computed the DC values of voltage and current for a half wave rectifier circuit, and we also computed the RMS values of voltage and current for a half wave rectifier circuit. So by using the same knowledge, we can substitute those values over here, and it will let you know that for the case of half wave rectifier circuit, in terms of percentage, we'll have about 40% of the value of rectification ratio will be about 40%. So it will be different for different types of converter circuit, rectifier circuits, for half wave, full wave, single phase versus three phase, and so on. Okay. Another term that is quite often associated with these type of rectifier circuits is known as form factor. It can be abbreviated as FF. This is basically the ratio of you can say RMS value to the average value. So it can be either the ratio of RMS voltage to RMS DC voltage, or it can also be the ratio of RMS current to DC current. Okay, so either of them can be used for this form factor. Another term that is associated with these converter circuits is known as peak factor. Peak factor is basically the ratio of the maximum value of current to RMS value of current. Okay. Another common term associated with these is known as the ripple factor. This is basically used to determine the amount of ripple present in a particular converter circuits. Okay, this is basically the ratio of like the AC quantity present in the output signal to the DC quantity of the output signal, and further the value of AC quantity can be determined by this equation. So this is how we can further calculate the value of ripple factor. Another term which may quite often be used in circuits where we also have a transformer used for isolation between AC and the output or the DC side, that is called the transformer utilization factor. So the transformer utilization factor is basically the value of the average or the DC power across the load divided by the AC power which is present on the, or the volt amperes that are present on the secondary side of the transformer. Okay, so this is the DC power or the average power that is present across the load or the output voltage and output current, and it is the ratio of the power that is present across the secondary of the transformer. So here Vs and Is basically determine the voltage and current on the secondary side of the transformer. So these are some of the basic quantities that could normally be required for different types of designs in the case of rectifier circuits. Okay, so you need to be at least familiar with these basic terminologies, while the ones that we introduced in the beginning, that is the DC or the average value and the RMS value, and in the same way the DC or the average power and the RMS power, so that will be quite frequently used in this analysis or this discussion.